Well, hello, my dear students. You're very welcome to lesson number 8, problem set number 6 of the dimensional analysis chapter. I'm your very own personal physics tutor, Dr. Rima McMullen. Today we are going to solve 2 more problems of dimensional analysis, and these are extremely important problems that will give you very useful insight into the subject matter. Problem number 1 says that the distance d that light can travel through fog depends on the mass density rho. This symbol here, it is called as rho, and it's a Greek symbol, and in physics it's typically used to represent volume density. What it means, we'll look at that in just a minute. Back to the problem, the distance d that light can travel through fog depends on mass density rho of the fog, the intensity I of the light, and its frequency f. And this dependence of d on rho, I, and f is given by this relationship over here. That's boxed in. So d is proportional to rho to the power a, where rho is mass density, times I to the power b, where I is the intensity of the light, and f is the frequency. D is inversely proportional to f to the power c. We are asked to determine the values of the exponents a, b, and c. So this problem can be solved in one of the two ways. You could either solve it using dimensional analysis, or you could solve it using SI units. So I'll show you both ways. Let's try solving it using dimensional analysis first. What are we given? We're given an equation d is proportional to rho to the power a, I to the power b divided by f to the power c. And our goal is to figure out the values of a, b, and c here. Now this kind of problems we have done quite a few times already. What do we do every single time? How do we begin these kinds of problems? The first thing we always do is replace the symbol of proportionality by a constant of proportionality k, where k is a constant of proportionality and it is dimensionless and therefore unitless constant. Constant of proportionality. It is dimensionless and therefore it is unitless. Alright, so we get now d, the distance equals k times rho to the power a, I to the power b, divided by f to the power c, which can be written as f to the power negative c. Now to solve it in terms of dimensional analysis, what you need to do is you need to write down the dimensional formula for all of these quantities into this equation. So on the left hand side, I have distance d. Its dimensional formula is m0 L1 T0. On the right hand side, you have k. K is a dimensionless constant. So we do not need to write down its dimensional formula, which will be, if you wanted to write, m0 L0 T0, which is basically just 1. So I'm not going to write it down. I'm going to write next the dimensional formula for rho to the power a times I to the power b's dimensional formula times f to the power minus c. Next, what I'm going to do is I'm going to pull these exponents out of the brackets. So it becomes dimensional formula for rho to the power a, dimensional formula for I to the power b, not a over here, times f to the power minus c's. Alright, now we do not know what the dimensional formula for rho, I, or f are. Let's figure those out on the side here. So talking about mass density rho, this is mass density. What would be its formula? It will be mass per unit volume. So its dimensional formula will be rho's dimensional formula equals mass dimensional formula divided by volumes. So that is m1 L0 T0 for mass divided by m0 L to the power 3 times T0 for volume. Combining all this gives you m1 L to the power minus 3 T to the power 0. So here we got rho's dimensional formula is m1 L minus 3 T0 brackets. However, we are asked to find the dimensional formula for not just rho, but rho to the power a. So I'm going to go ahead and put this dimensional formula on the right hand side and the left hand side to the power a. What does this give me? Bring the a inside the parentheses and that will give you m to the power a, L to the power minus 3a, and t's power is still 0 because anything which is a multiplied by 0 is still 0. Rho to the power a. Alright, very well. Next we have intensity, represented by letter I. This is defined as power per unit area. So the dimensional formula for intensity is I. Or before I do that actually, let me do something else here. Power is work per unit time. 1 over area. Okay. So the intensity's dimensional formula will be work's dimensional formula divided by time's dimensional formula multiplied by 1 over area's dimensional formula. So hopefully by now you do know that work is same as energy. This is the way I do it. Work is same as energy in terms of dimensions and SI units. One way to remember this is through the definition of energy. Energy is the ability to do work. So energy can be of different kinds. To get the dimensional formula for energy or work, what I remember is kinetic energy, which is 1/2 mv squared. This is what always helps me. So the dimensional formula for energy will be dimensional formula for mass times dimensional formula for v squared. This 1/2 doesn't matter, it's just a constant. So dimensional formula for W equals dimensional formula for mass times dimensional formula for v squared. Mass is just m and v squared gives you L squared times t to the power minus 2. So here we got the dimensional formula for work. This gives me dimensional formula for I equal to m1 L2 t minus 2 divided by m0 L0 t to the power 1 times 1 over a. A is m0 L2 t0. Let's see. Now here, this m1 divided by m0 divided by m0, what does this give me? M to the power 1. Next I have L to the power 2 divided by L to the power 2. These cancel out. We're left with this L to the power 0, which when comes up still remains L to the power 0. Lastly, I have t to the power minus 2 divided by t to the power 1. This t to the power 0 doesn't matter. This gives you t to the power 3. So here we got dimensional formula for I. However, what we want is dimensional formula for I to the power b. So raise this to the power b on both sides, and that will give you m to the power 1 times b is b, L to the power 0, t to the power, by the way, this is negative 3 here, negative 3b. This is I to the power b. Next I have frequency. In fact, I have 1 over f, correct? 1 over f is time period. Frequency is 1 over time period, so 1 over frequency is time period. I want the dimensional formula for 1 over f. So that is equal to dimensional formula for time period t, which is equal to m0 L0 t1. However, in the problem, I'm asked to find out f to the power c. So that will be equal to t's dimensional formula to the power c, which gives the dimensional formula to be m0 L0 t to the power c. So now I got dimensional formula for f to the power c, or rather I should say 1 over f to the power c, I to the power b, and rho to the power a. We're going to substitute these over here now. So the first one, rho, that's the easiest one, m a L minus 3a t0. Next, I have intensity. Intensity, let me write down this MLT. Then I'm going to go and look at the exponents here. B0 minus 3B. Last, I have F. This will give me M0, L0, T to the power C here. Moving on. M to the power A times M to the power B times M to the power 0. What does this give you? M to the power A plus B. Moving on to length, L to the power minus 3A times L to the power 0 times L to the power 0 is L to the power minus 3A. T to the power 0 times T to the power minus 3B times T to the power C gives you T to the power minus 3B plus C brackets. This is equal to M0 L1 T0. What do I do now? This we have done quite a few times by now. What we are going to do is we are going to compare. We are going to equate factors on each side that have same base. That is M to the power 0 on the left hand side equals M to the power A plus B on the right hand side. L to the power 1 on the left hand side equals L to the power minus 3A on the right hand side. T to the power 0 on the left hand side equals T to the power minus 3B plus C on the right hand side. Now, whenever the base is same, which is same in all of these cases, here I'm underlining the bases here. So for equation number 1, M is the base. For equation number 2, L is the base. For equation 3, T is the base. So base is same on each side, and when that is the case, what you do? You equate the powers. So equation 1 gives you 0 equals A plus B. Equation 2 gives you 1 equals minus 3A. Equation 3 gives you 0 equals minus 3B plus C. So from this, let me rewrite these real quick for you. Alright, so here I have rewritten these equations and I have also swapped left and right hand side of the equation. I need to solve for each of these exponents, which are A, B, and C. Now, which equation do you think I should start with? Is there an option? Is there even a choice here? I think the clear choice here is start with equation 5. Why? Because it's in terms of only one variable. So this gives you A equals minus 1/3. Once we have the value for A, then you need to move on to number 4. Why? Because 5 is solved and 6 doesn't have anything in terms of A. So 4 gives you B is equal to minus A. So B becomes equal to minus of minus 1/3, which is equal to 1/3. Lastly, equation 6, using this you can solve for C. So C is equal to 3B. Now B is equal to 1/3. So C becomes equal to 1. So here you have solved for A, B, and C. A is equal to minus 1/3. B is equal to 1/3. And C is equal to 1. So what was our relationship between D and rho, I, and F? It was D was proportional to rho to the power A, I to the power B, and F to the power C was in the denominator. So this becomes D is proportional to rho to the power minus 1/3 is for A, I to the power 1/3 for B, divided by F to the power C, where C is equal to 1. So this can be written as D is proportional to I divided by rho to the power 1/3 times 1 over F, which can also be written as D is proportional to I over rho to the power 1/3 times T to the power 1. Why? Because frequency is 1 over time period. In other words, 1 over frequency is equal to time period. Now, do I really need to write this power of 1? Nope, I do not need to. So here, we have solved for A, B, and C using dimensional analysis. But since I promised that I'll show you how to solve this problem using SI units. So how do I do that? We had already seen that we can write D equal to K times rho to the power A, I to the power B divided by F to the power C. Now just like before, we need to know the SI units of rho, I, and F. And I'm going to put these SI units in terms of the SI units of the most fundamental quantities, which are mass, length, and time. So that means whatever these units might be, I'm going to break them down. I'm going to keep simplifying them until they're all in terms of kilograms, meters, and seconds. Let's see how we do that. So first, SI units for rho, the mass density. That will be kilograms for mass divided by meter cube for volume. However, I want the SI units for rho to the power A. So this becomes kilograms to the power A divided by meter to the power 3A. Next, SI units for intensity. Intensity is power per unit area. Power is watts divided by area, which is meters. Now watts is actually uppercase W. That's the symbol for watts, but I'm writing it out. I'm spelling this out just for your benefit. Now power equals work per unit time. So 1 watt equals 1 joule per second. So instead of watt, now I'm going to write joule divided by second times 1 over meter square. Now again, joule is just uppercase J. And occasionally you will see even lowercase j written for joules. And seconds is just lowercase s. I'm spelling it out. I don't need to. Now energy or work. Work is equal to, or forget that. We already said that joule is the SI unit for energy and kinetic energy equals 1/2 mv squared. Now from here, 1/2 doesn't have any units. However, mass is kilograms. V squared is meter squared divided by second squared. Correct? Divided by this second times 1 over meter square, which is this one here. Where does this take us? Now we have this meter square at the top, which cancels out this meter square at the bottom. What does this give you? Kilogram divided by second cubed. How come? This second squared times this second. Now this is something that confuses a lot of students and they would get it wrong. So what we are saying here, after we have cancelled out meter, this becomes kilograms divided by second squared divided by second. So here, this is the blue one. And let's use green color. This is the green one here. So this can be written as kilograms second squared. And this over here, this is like saying it is 1 over second. So from here, you can very clearly see that second squared times second. Also, you might think that, let's say, if I had 1/2 divided by 2, would you say that this is equal to 1 because these two cancelled out? No, this would be wrong. Why? Because if you take half a pizza and divide it into half again, what do you get? You get 1/4, not 1. Similarly here, if let's say this kilogram was just equal to 1, like here, then I have 1 over second squared divided by second. It's the same thing now. 1/2 divided by 2. This is equal to 1/2 times 1/2. Or in other words, what you could say is that dividing is same as multiplying by the reciprocal. So when you're dividing 1 over second squared, this thing by the second, you're really multiplying by the inverse or the reciprocal of second, which is 1 over second. Here. Now, I know I'm showing this elaborately. Why? Because this is something where a lot of students would make mistake. That's why I'm emphasizing on this thing. And you make a mistake here, and you know that trap is going to be given there in those multiple choice answers. There will be a multiple choice where the seconds, one of them will cancel the other out. There will be one answer option that will be based on this for the SI units for intensity. These are incorrect. Anyway, so we want the SI units for I to the power B. That would be kilograms to the power B divided by seconds to the power 3B. So here we got the SI units for intensity. Last one is very easy. Last one is SI unit for 1 over F, which will be just seconds. But like you know, we want SI units for F to the power C. So this becomes S to the power C. Going back to our problem, the SI unit for distance, which is on the left-hand side, is meter, equals, this K over here is dimensionless, rho, this has dimensions of kilograms to the power A divided by meter to the power 3A, times I to the power B. We just saw this is kilograms to the power B divided by seconds to the power 3B. Lastly, I have 1 over F to the power C, and its SI units are S to the power C. Combining them, what does this give you? Kilograms times kilograms. Base is same, add the powers, becomes kilograms to the power A plus B. Then I have this meter to the power 3A, it comes up and becomes meters to the power minus 3A. Similarly, the seconds to the power 3B comes up and becomes seconds to the power minus 3B and combines with the seconds to the power C. So this becomes seconds to the power C minus 3B. And on the left hand side, I still have meter to the power 1. What do I do next? Now I want to compare the terms with same base on either side. So on the left hand side, I have meter to the power 1. Right hand side is meter to the power minus 3A. So that's meter to the power 1 equals meter to the power minus 3A. So here, these are gone now. But on the right hand side, I'm not done yet. I still have this kilogram to the power A plus B and seconds to the power C minus 3B. This is still left. So what do? I multiply left hand side by kilograms to the power 0. It's just 1. Anything raised to the power 0 is 1. So that gives me kilogram to the power 0 equals kilograms to the power A plus B. And same way, I still have the seconds to the power C minus 3B on the right hand side. So on the left hand side, multiply this by seconds to the power 0. That gives you seconds to the power 0 on the left hand side equal to seconds to the power C minus 3B on the right hand side. So just like before, m to the power 1 equals m to the power minus 3a will give you 1 equals minus 3a. Second one, kilograms to the power 0 equals kilograms to the power ab. It becomes 0 equals a plus b. And last one gives you 0 equals c minus 3b. So this first equation, this gives me a equals minus 1/3. Second one will give you b equals minus a, therefore b is equal to 1/3. And the last one gives you c equals 3b. From there c equals 1. So these are the same values of the exponents as we had before. A equals minus 1/3, b equals 1/3, and c is equal to 1. So here's your solution in terms of the SI units. You can utilize whichever method you prefer, unless you're asked to use a specific method. So what do you think about this? Was it a hard problem? Was it tedious? Was it easy? Am I explaining too much? Am I explaining too little? Is there anything I could do better? Please let me know in the comments, and please be kind to me and to others. All right, moving on to problem number 2. Problem number 2. In problem number 2, we are given a system of natural units, where in Planck's constant h, Newton's gravitational constant uppercase g, and the speed of light c. These are considered as the fundamental units. In such a system of units, which of the following answer choices is or are correct? So normally we consider mass, length, and time to be our fundamental physical quantities. In this problem, we're told that instead of mass, length, and time, consider Planck's constant, lowercase h, Newton's gravitational constant, uppercase g, and the speed of light, lowercase c. These are three fundamental constants instead of mass, length, and time. So we are now to figure out how to write length, mass, and time in terms of h, g, and c. And when we do that, when we write mass, length, and time in terms of Planck's constant h, gravitational constant g, and c, we call that mass as m subscript p, which is Planck's mass. And this length is L sub p, Planck's length. And T sub p is Planck's time. Now these units, Planck's mass, Planck's length, and Planck's time, which we're going to now evaluate, we are going to solve for those. We're going to figure out what they are. These were first introduced by Max Planck, the founder of quantum mechanics, in the year 1899. And what they are, I have shown that in a separate video, well, short videos, 3 short videos, but regardless, I'm going to derive them here now from scratch, okay? So let's see. Let's write down length in terms of C, H, and G. So what I'm saying is that length L is proportional to C to the power A, H to the power B, and G to the power C. And when I figure out A, B, and C, I have the dependence of L on C, H, and G. Once I know the dependence of L on C, H, and G, from there I could figure out which of these four, well actually A, B, and C, in all three of them L is proportional to square root of G. In D, L is proportional to square root of C. Which of these two options is correct? Let's see how to do it. Just like before, replace this symbol of proportionality by constant of proportionality K. Now the equation becomes C to the power A, H to the power B, G to the power C times this K, which is a dimensionless constant. Of proportionality. All right. Now let's see. You want to do this in terms of dimensions? Let's go ahead and do it in terms of dimensions. So on the left hand side, I have dimensional formula for L. Right hand side, K is dimensionless. So I have dimensional formula for C to the power A, dimensional formula for H to the power B, dimensional formula for G to the power C. On the left hand side, I get dimensional formula for L to be m0 L1 t0. On the right hand side, c is the speed of light, which is m0 L1 t minus 1 brackets to the power a, and h is going to be m1 L2 t minus 1 to the power b, and uppercase g's dimensional formula is m to the power minus 1 L to the power 3 t to the power minus 2, and this all is to the power c. Now, as before, we are going to bring the powers inside the brackets. That will give us m0 La t minus a, mb L2b t minus b, m minus c L3c t minus 2c. On the left hand side, I have m0 L1 t0. Okay. On the right hand side, m0 times mb times m to the power minus c gives you m to the power b minus c. Then I have L to the power a times L to the power 2b times L to the power 3c gives you L to the power a plus 2b plus 3c. Lastly, I have t to the power minus a times t to the power minus b times t to the power minus 2c. Brackets. Left hand side is m0 L1 t0. From here on, what we do, we have done it like million times before. Not literally speaking, but you know what I mean. So you get m to the power 0 equals m to the power b minus c. M to the power 0 on the left hand side equals m to the power b minus c on the right hand side. Why? Because the base is same, which is m. Likewise, L to the power 1 equals L to the power a plus 2b plus 3c on the right hand side. Last, t to the power 0 on the left hand side equals t to the power minus a minus b minus 2c on the right hand side. What do these three equations give us? They give us, and I'm going to swap left and right hand side, b minus c from the equation for m, which is number 1, equal to 0. Equation 2 gives you a plus 2b plus 3c equal to 1. Number 3 gives you a. Equation 3 gives us minus a minus b minus 2c equals 0. So now we have to solve for a, b, and c, correct? The last two equations, if I add them, a's cancel out. I'm left with b plus c equals 1. This equation, along with this number 4, and call this as number 5 here, b minus c equals 0 and b plus c equals 1. Add these up. What do you get? C's cancel out. 2b equals 1, b equals 1 half. Now, once I have the value for b, then from this equation over here, b is equal to c. This gives you c is also equal to 1 half. Now I know b and c. I need to solve for a now. So from this equation over here, let's call it as number 6, which is minus a minus b minus 2c equals 0. Go ahead and add a to both sides, and after that swap left and right hand side. What does that give you? A equals minus b minus 2c. So b is equal to minus 1 half and c is also equal to minus 1 half. This gives you a equals minus 1 half minus 1 equals minus 3 halves. So here now we have our a, b, and c. What are they? A is equal to minus 3 halves, b is equal to 1 half, c is equal to 1 half. What was our equation? We said L is equal to k times c to the power a, h to the power b, and g to the power c. Now it turns out that this k is equal to 1 over 2 pi under the square root. C to the power a. C to the power a means c to the power minus 3 half. H to the power b, which is 1 half. G to the power c, which is also 1 half. How can we write this? This is written as 1 over 2 pi hg divided by c cubed, all of this under the square root. Now this h over 2 pi, this is given a special name. It's called as h bar or reduced h. So this equation now becomes L subscript p. It's Planck's length. It is h bar times g divided by c cubed. So L is proportional to square root of g, inversely proportional to square root of 1 over c cubed. So L is proportional to square root of g. That means this is correct, this is correct, this is correct, but this is not. Why? Because L is proportional to 1 over c cubed's square root. Now out of A, B, and C, we need to check for M and T. Which of these are correct? Okay, so we're going to next solve for Planck's mass. How do we do that? Mass is proportional to c to the power a, h to the power b, and g to the power c. So I'm keeping the exponents for c, h, and g to be same as I had in the first case for L. Look here. Same exponents. That means on the right hand side I'll have the same equations. If you don't believe me, try it for yourself. What I'm saying is that here, m is equal to k times c to the power a, h to the power b, g to the power c. Plug in the dimensional formula for c, h, and g, which I have shown you here before, and solve for this. You're going to get exactly the same thing on the right hand side. Left hand side in this case, however, is going to be different. How? In the case for L, left hand side was m0 L1 T0 because it was length. But now we have mass on the left hand side, so this is m1 L0 T0. K here is dimensionless. And c to the power a, h to the power b, and g to the power c will give you exactly the same equation, which I do not have memorized, but I have it written here. This will give you m to the power b minus c, L to the power a plus 2b plus 3c, and I do remember this, t to the power minus a minus b minus 2c. Now, m to the power 1 equals m to the power b minus c. L to the power 0 equals L to the power a plus 2b plus 3c. Last, t to the power 0 equals t to the power minus a minus b minus 2c. So from here, you know what I'm going to do next. I get b minus c equal to 1, a plus 2b plus 3c equals 0, minus a minus b minus 2c equals 0. And our goal is to solve for a, b, and c. Just like before, let's add these two bottom equations. This cancels out a, and we're left with 2b minus b is b, 3c minus 2c is c, equals 0. So now we have these two equations, 1 and 2. 1 is b minus c equals 1, and the number 2 is b plus c equals 0. Add these up and you get 2b, c's cancel out, equal to 1. 2b equals 1, which means b is equal to 1 half. From equation number 2, c is equal to negative of b, means c is equal to minus 1 half. We still have to figure out what a is. So from equation, let's call this as equation number 3, minus a minus b minus 2c equals 0. Add a to both sides, and after that swap left and right hand side. That will give you a equals minus b minus 2c. What is b? b is equal to minus 1 half minus 2 times c. c is minus 1 half. That gives us minus 1 half plus 1, means it is equal to 1 half. And in the case of L, a was equal to minus 3 halves. Okay. So now we got a to be 1 half, b to be 1 half, and c to be minus 1 half. What does that make m? m is equal to k times c to the power a, h to the power b, g to the power c. And it turns out that this k, the constant, is again 1 over 2 pi under the square root. C to the power a is 1 half, h to the power b, b is also 1 half, g to the power c, c is minus 1 half. Now this can be written as c times h divided by 2 pi times g under the square root. This gives you c h bar divided by g under the square root. This is Planck's mass. So mass is proportional to c, inversely proportional to g's square root. Let's look at our options. M is proportional to square root of c, this is correct. M is proportional to square root of c, this is also correct. M is proportional to square root of g, this is incorrect. So now we have to see out of these two if they're both correct or just one of them is correct out of A and B. We're going to solve for Planck's time now. This is going to be T is proportional to c to the power A, h to the power b, and g to the power c. Just like before, we get t equals k times c to the power a, h to the power b, g to the power c. Writing in terms of the dimensional formula, left hand side is m0 l0 t to the power 1, and right hand side is going to be m to the power b minus c. Okay, that's a bad looking c. b minus c, l to the power a plus 2b plus 3c, t to the power minus a minus b minus 2c, parentheses. Alright, this will give you b minus c equals 0, a plus 2b plus 3c equals 0, minus a minus b minus 2c equals 1. Now, how I got these three equations, if you do not know, look at how I solved for length. Adding the last two equations, I get b plus c equals 1. Using 1 and 4. 1 plus 4 gives you b minus c equals 0, that is 1. b plus c equals 1 as equation number 4. Add these two up. C's cancel out. You get 2b equals 1, or b is equal to 1 half. Now from equation number 1, b minus c equals 0, or you can say c equals b, c is equal to 1 half. Then we have equation number 3, which was minus a minus b minus 2c equals 1. From here you will add a to both sides and subtract 1 from both sides, and then swap left and right hand side. You will get a equal to minus b minus 2c minus 1. b is equal to 1 half, so you get minus 1 half minus 2 times c. c is equal to 1 half, and there's minus 1 here. So you get minus 1 half minus 1 minus 1. These twos here cancel out. What do you get here? Minus 5 halves is equal to a. So we got a to be minus 5 halves, b to be 1 half, c to be 1 half. So Tp, which is Planck's time, equals k times c to the power a, h to the power b, g to the power c. And this k here is also 1 over 2 pi. So c to the power 1 half, h to the power 1 half, g to the power minus 5 halves. How else can we write this? This can be written as ch divided by 2 pi k is again equal to 1 over 2 pi times c to the power a. A is minus 5 halves, h to the power b, which is 1 half, g to the power c, c is also 1 half. We can write this as h times g divided by 2 pi times c to the power 5, all under the square root. And by now we know that h over 2 pi is reduced Planck's constant, h bar times g divided by c to the power 5 under the square root. This is Planck's time. So t is proportional to square root of g. Let's go to our answer options. And here, for b, t is proportional to square root of g, m is proportional to square root of c, l is proportional to square root of g. So b is correct. Once again, I'm going to write here LP. LP is equal to h bar g over c cubed under the square root. Then we have mass, MP. That is equal to h bar c over g. And last is TP. That's going to be h bar g over, not cubed, it's 5. Now, as far as their values go, Planck's length is approximately equal to 1.616 times 10 to the power minus 35 meters. Planck's mass is 2.176 times 10 to the power minus 8 kilograms, and the time is 5.391 times 10 to the power minus 44 seconds. Now, just for the sake of comparison about how small or how big these numbers are, the size of a hydrogen atom is about 10 to the power negative 10 about meters, and size of a proton is about 10 to the power minus 15 meters. So the Planck's length, it is approximately 25 order of magnitude smaller than the size of a hydrogen atom, which is the smallest atom. And it is about 10 to the power 20. It's times smaller than the size of proton. In other words, a proton is 20 orders of magnitudes larger than the size of Planck's length. So Planck's length is actually incomprehensibly smaller length. We have not been able to reach this length in any experiments thus far. Likewise, Planck's time, it's a very, very small time. Again, not attainable yet in any labs. Planck's mass, though, it's a large mass as compared to, mass of proton or mass of an electron. Electron's mass is 9.1 times 10 to the power minus 31 kilograms, and proton is about 10 to the power minus 27 kilograms. So this is way, way larger than those masses. But the Planck's length and Planck's time, these are very, very small numbers. Okay, so this was our chapter on dimensional analysis. I hope that you found it useful. And if you did find it useful, please subscribe to the channel. Like this video, it motivates me more than you would know. This is my part-time hobby work, and the more encouragement I get, more likely I'm to make these videos, which I do enjoy a lot actually. So I would really appreciate your support. Thank you. I'll keep making these videos for you. I'm coming again very soon with videos on measurements, uncertainty, error, and soon after that we're going to move on to my favorite topics, vectors. All right, see you next time. Until then, keep enjoying studying, keep learning physics, keep learning, keep growing.